you can't use the shortcut because we don't know, just by looking at this, we have no idea. Is that one eigenvalue going to give me two different eigenvectors or one? Well, this method can only ever give you one. Okay, so we have to do it the long way because we can't tell if we will end with one or two eigenvectors. Okay, we know if we have two different ones, they're each going to give us a different eigenvector, but we don't know if we have the same eigenvalue twice. Are we going to get two distinct eigenvectors, or is it only going to be one? You don't get into all the theory that we, cover about that. That's more in Math 1600. But, you should know that you could get one or two, just so that you know in case for the exam, right? Okay, so example 7, halfway down to 59. So given matrix A, okay, which has eigenvector -1, 1, what is the corresponding eigenvalue? Okay, so what is the corresponding eigenvalue? Okay, so we can do this in a few different ways, right? I think I left room. Yeah, I left you room to do more on this page. So one way we can do this is by going through the process of, finding the characteristic polynomial, finding the eigenvalues, and seeing what the eigenvectors are. So we'll do that first, and then I'll show you a trick after, okay? So what I want you to do here is, if this is our matrix, A, B, C, D. So if you do like the trace and determinant method, then I want you to practice it once here. So trace and det, and then the equation. If you don't like it, you can go straight to long method. We'll get to it in a minute, okay? So I want you to do that. So regardless of method, I want to get your characteristic polynomial, and I want you to factor it and find me your two. This one will have two different or distinct eigenvalues. Okay, so go for it, and then I'm going to show you how to find the eigenvectors, the short and the long way. Okay, So let's see what you came up with here. So the trace, and of course you don't have to write the formulas once you know it, but 2 plus 3, so that's going to be 5. Determinant AD minus BC is 6 minus 0, so 6. So our formula, characteristic polynomial, is lambda squared minus the trace times lambda plus the determinant. So I'm going to add to negative 5 and multiply to positive 6. So I need lambda minus 2 and lambda minus 3 in any order. So my eigenvalues should be 2 and 3. Okay, questions? Okay, so eigenvectors, well, let's just call lambda 1, 2, and lambda 2, 3. So if I've got 2, then, and my matrix is here, so I can say my v1, my eigenvector, is b over lambda minus a, unless it's the 0 vector, and then I can switch it. So b for my matrix is 0, and lambda is 2, so 2 minus a is 2, gives me the 0 vector. So that's an example of one that won't work. So we can use lambda minus d and c. So my vector is lambda is 2 minus d. D in the matrix is 3, and c is 1. So negative 1, 1 is our eigenvector. Or 1, negative 1. Remember, any multiple is also correct. Okay, so what about my eigenvector that goes with lambda 2 is 3? Well, b over lambda minus a. B is 0. All over lambda is 3 minus a is 2. So 0, 1 is my second eigenvector that corresponds to eigenvalue lambda equals 3. So the question wanted, what is the eigenvalue that went with negative 1, 1? Well, that eigenvalue that went with negative 1, 1 was 2 then. So that's A. Okay, I'm going to also show you something else when you come back from break. So it's 6:20. So come back at 6:35 and we'll carry on. Go get some food, drinks, whatever you need. Okay, I'll see you back shortly. Okay, welcome back everyone. I hope you had a good break. So we're just going to continue on with eigenvalues and eigenvectors, okay? So turn back to page 259. So after making you do that, I'm going to show you a little trick for this question. Then I will show you it the long way just for you to practice the method. But for this one, because it gave you the eigenvector and wanted to know the eigenvalue, we technically don't have to go through all the work, right? We could say we know that AV equals lambda V, right? For an eigenvalue and eigenvector. So what we could do is say 2013 is A times the eigenvector. We can just say, negative 1, 1, because they told us, equals lambda times negative 1, 1, right? We know V, so we can put it here and here. And then really, we're just trying to find out what this number is. But since I taught you, how to multiply this, we can just say first times first plus second times second. So 2 times negative 1 is negative 2 plus 0 times 1 is 0. And on the bottom, 1 times negative 1 is negative 1 plus 3 times 1 is 3. Well, guess what? We have negative 2, 2 is lambda negative 1, 1. Well, just look at it by inspection. What's lambda? Something times negative 1, 1 has to be negative 2, 2. Then the something is clearly just 2. So see how fast that was? So if they give you the eigenvector, use your formula that A times V equals lambda times V. Put the lambda as lambda, fill in everything else with your eigenvector, and then, you can solve it by, we would just say by inspection there kind of thing. Okay? So just something to keep in mind, okay? All right, so I'm going to show you the long method just for practice. So, assuming you don't have this eigenvector, what would you do kind of thing? So we need det A minus lambda I equals 0. So remember, we take our A and we do minus lambda times I, which remember we talked about lambda times I is really just lambda 0, 0 lambda. Okay? So now we've got det 2 minus lambda. All right, I want you to do the rest here. What would it be? Fill in the rest. And then I want you to do your AD minus BC and see what you get for your characteristic polynomial here, okay? Okay, so we've got 0 minus 0, 1 minus 0 is 1, and 3 minus lambda. We know it's AD minus BC equals 0 for the determinant. So we've got 2 minus lambda, A, times D, 3 minus lambda, minus, we get lucky, BC is just 0. So really, because that's 0, we don't even have to factor, right? Because we can just say, oh, this equals 0, then lambda is 2. This equals 0, then lambda is 3. Okay? So lambda equals 2. So again, we can either do A minus lambda IV equals 0 or AV equals lambda V. So it's up to you, right? So if we look at this matrix right here, that's A minus lambda I. So if we take A minus lambda I and put lambda is 2 in there, then what's our matrix? Well, we're just going to get 2 minus 2 is 0, 0, 1, and 3 minus 2 is 1. And then V is just vector V, V1, V2, equals the 0 vector. So what does each row tell us? Well, the top row dot that vector would tell us that 0 V1 plus 0 V2 is 0. The bottom row is going to tell us 1 times V1 plus 1 times V2 is 0. So this one's not too useful, right? Because that would be true for any number, right? 0 times anything plus 0 times anything is always 0. From this one, I can say that V2 is equal to negative V1. So that means my vector can be V1 and then V2 is negative V1. Or I can say some number t times 1 negative 1. And of course, at that point, I could stop this question because I have the eigenvector is the one I got, right? So then I kind of know already that it's 2. Okay. Where's the 0 and 0 matrix from to form these equations? I'm not sure what you mean by the 0 matrix. So we have this matrix that we did earlier, A minus lambda I. And to find the eigenvector, we have A minus lambda I times V equals 0. So if our lambda is 2, when we put 2 in here, 2 minus 2 is 0. V is already 0. 1 is there. And 3 minus 2 is 1. And that's just this formula. Is that what you mean? I'm not sure. No problem. You're welcome. So if you did want to find the other one, then what we would have to do, so I know we don't need to, but if you did, lambda was 3 was the other one. So to find the eigenvector, well, if A minus lambda I, I'm just going to write this because it's at the top of my page. I know it's so annoying for you guys for me to move up and down a million times. So this is at the top of my page. So if I put 3 in here, then my matrix is going to be 2 minus 3, so negative 1, still 0, still 1, and 3 minus 3. So if I say that is times V, vector V, equal the 0 vector, what would that tell us for the other vector? Well, let's see. If we take the first row and dot here, so, first times first plus second times second, negative 1 times V1 plus 0 V2 is 0 equals 0. So if negative V1 is 0, then V1 is actually 0. The bottom is going to tell me the same thing. It's going to tell us 1 times V1 is V1 plus 0 equals 0. So what does that mean about my vector? Well, that means my vector, the eigenvector that goes with 3, is going to be V1 is 0 and then V2. Or in other words, t times the vector 0, 1. So the eigenvector that goes with 3 would be 0, 1, or any multiple, of course, of that. And if you take a look, is that what we got before? Yes, right? Using that trick method, we got 0, 1. Okay. So You've seen a quick method, a long method, and then kind of a little trick that I showed you. If you know the eigenvector, right, then you can just do AV equals lambda V and kind of look at it and solve by what we would call inspection. Okay, so we're going to practice it, okay? So this is, one of the harder sections because it does have a lot to it, but it's very important also for the last, little bit of the course that we haven't finished yet, okay? Okay. So for this one, I wrote it a bunch for you just to save you some writing. So find the characteristic polynomial and eigenvalues. So if we want to do the shortcut, well, the trace would be, your A plus D. 2 plus 2 is 4. Det A, AD minus BC would be 4 plus 3 is 7. So our polynomial, characteristic polynomial, lambda squared minus the trace of A times lambda plus det A. So lambda squared minus 4 lambda plus 7. Now, when we use the quadratic formula this time, we get lambda equals negative b, so negative 4 is plus 4, plus or minus square root b squared, well, negative 4 squared, remember, is positive 16, minus 4 times a times c, so 4 times 1 times 7, all over 2a, which is 2 times 1. Now, 16 minus 28, think about that, right? That's going to be a negative. Okay, so 16 minus 28 under the root is negative 12. So we have 4 plus or minus root of negative 12 over 2. Now remember, the root of negative 12, well, you can do it in steps or you can do it all at once. So the root of negative 12, we could say root 4 we can do in our head, root 3 we can't, and root negative 1. So we can do the product for all three. Root 4 is 2, so it's 2 root 3 times I. And so that's what I get right here, 2 times root 3 times I. So once we have this, if you think about what I've got here, I'm just going to space it out more. If all three of these numbers can be reduced, then you can do it. So because both of the top numbers, the 4 and the 2 in front, can both divide by 2, I can do it. But if it was like this, I couldn't do anything, okay? So keep that in mind. And you can never divide by 2 under a root. So don't ever go there, okay? So really, we're just taking out a common factor of 2 from this term and this term. Okay, so it's 2 plus root 3i, 2 minus root 3i. So those would be called, the two complex conjugates. Okay, now finding the eigenvectors. Well, again, if you do get, something like this that's on a multiple choice, then the trick method is a lot faster, especially when you have i's, right? So if we have our matrix A, B, C, D, well, if this is our first lambda, we know that the eigenvector can be b over lambda minus a as long as it's not 0, 0. If it is, then we switch to the other one. So b is negative 1. Lambda minus a is 2 plus root 3i minus a is 2. Well, the 2's cancel, the 2 and negative 2, and we get negative 1 and root 3i. If we do the other complex conjugate, 2 minus root 3i, b is on top, b is negative 1, all over lambda minus a. So 2 minus root 3i minus a, which is 2. And notice, really, these are, the same. It's just that one is negative 1 and one is, over positive root 3i and one is negative 1 over negative root 3i. And this is just multiplying all the components by a negative 1. Okay. So, equivalent answer. Okay. So negative 1 over root 3i, and the other one is, 1 over root 3i. All right, now, long way. Well, we can also, instead of doing that shortcut, we can use our formula AV equals lambda V. Now, The one that I showed you before, a lot of people do like this one here better when they're not complex, but it tends to be a lot harder when they are complex. So when you have i's involved, roots of, negative number to get your I, usually this one's a little bit faster. Okay. I don't like how that I looks like it's under the root. I think that's just in the equation editor. So just, it's like root 3 times I. Kind of looks like it's under it there. So just make sure you know that it's not, okay? Okay. So if I do AV equals lambda V. All right. Well, here we've got, there's our A, and then we've got V. So let's see. So here's A, 2, negative 1, 3, 2. And V equals, and then lambda V. Okay. So you can either use this or you can put it into the other one. So from this one, if you look at, this equation, we're going to get 2 times V1 minus V2. And in this case, we can just say that that's going to be lambda, because this is my lambda, times V1. So what we're doing is we're just kind of thinking like this is just a lambda for a minute. And what we're going to do is sub the lambda in later. So if you like, it's kind of like saying this. V1, V2, like this. So we're kind of coming up with a generalization that works all the time. And then we put the lambda in after. So think about the top row. The top row, 2 times V1 minus 1 times V2. 2V1 minus V2 equals the top over here. Okay, so that's the top. And then for the bottom, well, then I've got this times this equals this. So 3 times V1 plus 2 times V2 equals lambda V2. So see, I have that equation. Now, sub in the lambda. So we're going to do 2 plus root 3i. So we have here, from this, we can say, if I want to solve this, let's say, kind of simplify it, 2v1 minus lambda v1 equals v2. So I'm moving the v2 across to this side. So now from here to here, see how they both have a v1 in front? Common factor it. So take out the v1. Then v2 is v1 times 2 minus lambda. So now when you put this in, things are going to cancel out nice. Because when this goes right here, look at what my v2 is going to be. 2 minus, and then look, if your lambda is right here is 2 plus root 3i, then it's 2 minus 2 plus root 3i. Well, 2 minus 2 is gone, isn't it? So it's just 0 minus root 3i. Let v1 be a 1. And then it's just 1 times this, which is just negative root 3i. Okay, and your v1 is 1. So your vector, your vector is v1, v2, is going to be 1 and negative root 3i. So same thing as before. Now, I think ours was the opposite sign, right? Yeah. So negative 1 on top. So multiply them both by negative and see the answer. Okay. So, it's up to you which method you want to use. Either way, yes, it's a pain, right, to do it the long way when you have an I, because it's just a lot of work, right? Okay, so the other long method that you can use, I did leave it, I left some space here. So if you don't like that one, Your other choice is just to put a minus lambda I v equals 0 like we did before. And remember, a minus lambda I what was our matrix? Let's see. Oh, I don't think I did it yet, right? I don't think. So a minus lambda I. So a was 2, negative 1, 3, 2 minus lambda times I. So that's how I got that matrix. So that is from there. And then I put my lambda in. So if lambda is 2 plus root 3i, and that goes there and there, then it's 2 minus 2 plus root 3i, negative 1, 3, and 2 minus 2 plus root 3i. So think about the canceling here. 2 minus 2 is 0. So that's just negative root 3i. Negative 1 stays, 3 stays, 2 minus 2 is 0, and then negative root 3i. So that's what we've got to solve. And from there, again, we can do the top, this times this, so negative root 3i v1 minus 1 v2 equals 0. Easiest way to solve that would be to solve probably for v2, right? Bring the v2 across, it becomes positive. Let v1 equals 1, then v2 is negative root 3i. So you can see how we got the same vector in 3 different ways. So you've got to decide, what do you like better? Which method makes the most sense to you? Now, of course, you can't only pick the shortcut method because you don't have that choice, right? If you'll get a long answer somewhere, I guarantee it, you're going to have to do eigenvectors on the long answer somewhere, right? So, of course, you can use your trick method here, the b over lambda minus a, or the other formula. If it's a 0, 0 vector, then you know it can't be that. You can obviously use it to check, and you can use it on your multiple choice. But of the two long methods, you have first choice. If you want to do AV equals lambda V, if you want to do it the way they taught you in class, then you do A V1 V2 equals just the letter lambda V1 V2. Make the equations, and then look at which one you can solve easier. So when we did 2v1 minus v2 equals lambda v1, and then of course in this one I solved for v2, and then I took a common factor out. And then once I got the equation for v2, I put the particular lambda that I had, 2 plus root 3i in. Of course, I could do the same thing for 2 minus root 3 to get 2 minus root 3 to get the other one, right? 2 minus root 3i. And so then let v1 equal 1 and find v2. So to find the other eigenvector for lambda 2 equals 2 minus root 3i, you can substitute that in. Okay? So if you like that method, great. If you don't like it, then you can just do it the same way we would do, if it's not complex, okay? Which is find a minus lambda times I. In that matrix, put your lambda in, get your simplified matrix, set it up as, that answer times vector v, v1, v2 equals 0, 0. And, you may have to look at both rows. You may just have to look at one row, right? It just kind of depends on what the numbers look like. Usually one of them for complex will work. Now, this at the bottom here is just talking about how often we get, eigenvectors that don't really look the same for complex roots, but they are the same. So always remember, here, if we have negative 1 root 3i, it's an eigenvector of matrix A with eigenvalue 2 plus root 3i. If W is I in root 3, what's the value of AW? Well, what you notice here is that W does not look like V, does it? It looks very different. But if you take W and multiply by I, you get I times I on the top is I squared, which is negative 1. and root 3i. And guess what? Same vector. So if v and w are equal, remember, AV is lambda v, then if w is the same, then AW is just lambda times w. Same thing as lambda times v. So our lambda is right here, and then there's our vector v or w. And, we get the same answer. So it's, kind of up to you what you do. But if you get a vector on your exam, let's say this is your vector, and none of the multiple choice have that vector, but let's say the I is on top of their vector, then try multiplying by I, okay, on the top and bottom, and that will be an equivalent vector. And of course, the i's will kind of switch places because remember, I times I with the bottom, component, I times I is going to be I squared, which is going to be -1, and, that whole concept. All right, here we go. You ready? Find the eigenvalue and the eigenvector for A plus BI. So we kind of know at this point, if they're saying I, that I guess it's going to be, unfortunately, complex, right? And we want the positive one. Okay, so first of all, well, if they say A plus BI, I mean, we don't know what the eigenvalues are. So first, right here, can you find me the eigenvalues? And I want you to do the long method only here, okay? We've done enough practice with the shortcut. You've got more paper here, and then, so you've got 2 pages to do the whole question. So eigenvalue and eigenvector. So right now, I want you to try the eigenvalues, and then I'll show you the answer, and then we'll talk about the eigenvector, okay? So have a go at it. Okay, does anyone want more time for the eigenvalues? If you do, just, type yes into the Q&A and I can wait more. hard when I can't see you. Okay, good. Okay, so if we've got our debt, a minus lambda I equals 0. So determinant a, so 2, negative 4, 5, 5, minus lambda times I, so lambda 0, 0, lambda, equals 0. So don't forget, 2 by 2 formula is just AD minus BC for the determinant. So here we subtract 2 minus lambda. Negative 4 minus 0 is just negative 4. 5 minus 0 is 5, and 5 minus lambda. So let's see, we've got 2 minus lambda times 5 minus lambda, so that's AD, minus BC is negative 4 times 5, so that's going to turn to a plus, right? So we FOIL all that out, we get 10 minus 2 lambda minus 5 lambda plus lambda squared and then plus 20. So if I collect terms here, I've got what? Negative 2 and negative 5, so minus 7 lambdas and 20 and 10, so plus 30. So if they only asked for this, it would be called your characteristic polynomial. Okay. So I would love to factor it, but I don't think it does, right? Because, 30, we could do lambda minus 10, lambda plus 3, and that would be a minus 30, right? So it doesn't factor, right? There's nothing that will work because to multiply to 30, we could use 15 and 2. That can't make 7. And to multiply to 30 is only 10 and 3. It have to be negative 10 and positive 3, which will multiply to a negative. So unfortunately, it's the quadratic formula. So lambda is negative b plus minus square root b squared minus 4ac all over 2a. So if I add a 1 in there, that's my a. B is negative 7 and c is 30. Okay, so negative b. So negative 7 is 7 plus minus square root b squared. So negative 7 squared is positive 49 minus 4 times a is 1 times c is 30. All over 2 times 1, so really just 2. Okay, so what's under my root there? I've got, looks like 49 minus 120 then, right? So that's going to be 7 plus or minus root negative 71 over 2. So we can say 7 plus or minus root 71i over 2. So final answer for lambdas would be 7 plus root 71i over 2. And the complex conjugate, 7 minus root 71i over 2. So those are our two answers there. Okay, so I'll put up two different long answers. So what I want you to do is think about which one did you like better. One of them, we did on page 262, where we kind of rearranged it with lambda in general first and then put the lambda in. Second one, we did the same as before. We took our a minus lambda I, we put the lambda in right away and solved it like that. So go ahead, pick one or the other, and I want you to find the eigenvector, but just for the positive, okay? So just strictly on the positive, what would your eigenvector be? If you need more space, it's over here. So in a minute, well, in a few minutes, obviously, I'll take up both possibilities, okay? So pick your method and go for it here. Okay, does anyone want more time? Okay, so for those of you who picked the one that I showed you that they did in class where they just kind of called it lambda first, so we can call like this long method 1, I guess. So we have our matrix. So we had 2, -4, 5, 5. So we've got 2v1 minus 4v2 equals lambda v1. And the bottom, 5v1 plus 5v2 equals the bottom is lambda v2. So if you just look from this one, you would have 2v1 minus lambda v1 equals 4v2. And if we solve for v2 here, let's see. So that one would be, so if I take out, I guess, a v1, so I've got 2 minus lambda times v1 equals 4v2. And I have to sub in my lambda was 7 plus root 71I over 2. Okay. Well, that's lovely. So v1 times 2 minus 7 plus root 71I over 2. Okay, so that would be 2 minus 7/2 plus root 71 over 2 I. So if I let v1 equal 1, then I've got 2 minus 7/2, and I guess it's minus this whole thing. So 2 minus this lambda would be minus root 71I over 2 equals, and then this is 4v2. Okay, so let's see. I think I have to go to the other page. So this would be what, 4/2 minus 7/2. I guess I can do that here. 4/2 minus 7/2, so that's -3/2 minus root 71I over 2 equals 4v2. Okay, so that means my v2 has to be that over 4, right? Okay, so if we're dividing by 4, it's like multiplying by a quarter, so it's kind of like -3 over 4 minus root 71I over 4. So my vector is v1 was 1 and v2 is this mess. Okay. So if you prefer the other method, which personally I like the other one, it's up to you though. So a minus lambda v equals the 0 vector. So we take my a, and we already did a minus lambda v. So it was right here, right? That's already a minus lambda v. So it's just 2 minus lambda, -4, 5, 5 minus lambda. So that's already that. And so if I put the lambda in there, which was 7 plus root 71i, I think. Yeah, 7 plus root 71i over 2. So if we substitute that in there, and we're going to call it, v1, v2 equals the 0 vector. Okay, so if I put that in there, then I've got 2 minus 7 plus root 71i over 2, negative 4, 5, and then 5 minus 7 plus root 71i over 2. I think I'm actually going to run out of room. So 2 minus this, so that's going to be still just kind of like 4 over 2 minus 7 over 2 there. I'm just trying to think of, I could just look at this row if I wanted. See if that's faster. 5 times v1, and then plus all of this times v2. Just want to make sure. I have this as 3 minus this. Is it 5 or 3? Did I write that down wrong? No, it's 5. Okay. Okay, so if we dot this times this plus, and then 5 minus 7 plus root 71i over 2, v2 equals 0. Okay, so let's see, this is 5v1 equals, so if I bring this over, maybe I'll simplify this first. So 5 minus lambda times v2. So that's 5 minus 7 halves minus root 71i over 2 times v2 equals 0. I'm trying to think if there's a quicker way to do all of this here. It's ending up being a lot more algebra than I was anticipating here. So this times this. And this is all times v2. Not so nice, is it, guys? I could, I guess, write this all over 2. This would be like 10 halves. So 10 halves minus 7 halves, so that's 3 halves minus root 71i over 2 v2. So if I bring, let's say, the v1 over, I could say, maybe I should just let, v2 be 2. Maybe that to get rid of the fractions. So if I multiply this, I've got, 6 divided by 2, so that's just 3. And these 2's will cancel. So 5v1 is negative 3 plus root 71i, and that would be over 5. Man, that is a horrible, horrible question there. I'm just looking at why I have a 5 instead of a 4 there. Where I got the 5 from there. I'm going to check that after, guys. So in this method, we have v1 2 minus lambda equals oh, that's because I used the top equation versus the bottom. Okay. All right, I'm going to have to check that after just to make sure. Because, of course, they're going to look different because I used two different methods, right? We've got the i's in different places. So this one has v1 as 1, v2 as this I on the bottom, this one's the opposite, right? And v2 was 2. Oops, that's our v1, v2. Okay, so you can see they can be very, very horrible in terms of the algebra. You miss one sign or one fraction or anything and you're in trouble, right? Now, I haven't seen them give ones this complicated, but I mean, they were in your notes this year where they showed you, the long method of just putting land in and subbing in after. Because they took everything 3 by 3 out, I feel like they're probably going to give you a really hard 2 by 2. Because normally 2 by 2s are pretty simple, right? And then, your harder question would be your 3 by 3. So since they took out 3 by 3 determinants, inverses, eigenvalues, everything, you're probably going to get a pretty crazy one. Again, definitely, you can use the trick method to check though, like even on your rough work, right? And keep in mind again that if you have i's on the top and they have i's on the bottom, then you can play around between the answers by multiplying by I on the top and bottom. Okay, last one. How do you get two vectors from one eigenvalue? Okay. Well, in this case, if I do det a minus lambda I, so we've got 1, 0, 0, 1 minus lambda I equals 0. So we've got 1 minus lambda, 0 minus 0, 0 minus 0, and 1 minus lambda. Okay, so now, well, just the usual at the start. Do your whole AD minus BC equals 0. And notice it's really just 1 minus lambda times 1 minus lambda minus 0. So do we really need to write minus 0? No, of course not. So notice that there's only really one eigenvalue, right? It's like a double root. So the eigenvalue 1 occurs twice. So there's no shortcut method allowed, right? You can't use any shortcut because it's never going to show you both eigenvectors if there are two. So we can use AV as lambda V or A minus lambda V equals the 0 vector. So if I take my A times V, V1, V2 equals, and then here lambda is 1 times V. So this is my A matrix. This is the vector V, V1, V2 equals 1 is my lambda, V1, V2. Okay. So I want you to write out what are your equations. You know how to do this, top row dot V1, V2, and then do the bottom row. What do you get here? So we get 1 V1 plus 0 equals V1. So V1 equals V1. Well, that tells us nothing, right? V1 equals itself. Second one, 0 V1, so 0 plus 1 V2 equals V2. So we didn't get that V1 is 0 or V2 is 0 or anything like that. We're just getting V1 is itself and V2 is itself. So guess what? That means that both V1 and V2 are what we call like a parameter. Remember when we had those t's in our answer? So they can take on any value. So what we do is we say let V1 be a different letter than V2. So my vector V1, V2 is ST, where S and T can be any real numbers. Okay, so that one is definitely tricky. All right, so that is eigenvalues, eigenvectors, and characteristic polynomials. Okay, so flip through. So next is K. K is on 269. So in K, we're going to have, systems of recursion and solving to find sometimes I call it the explicit age structured model. So we can be dealing with questions like juveniles and adults and things like that. Okay. So you're always going to have to find your eigenvalues and eigenvectors first, and then we'll find the constant. So we talked about, finding C1 and C2 before. And then this will be our explicit solution. So it'll be xt is C1 V1 lambda 1 to the t plus C2 V2 lambda 2 to the t. Now they use lambda for one and u for the other, which drives me crazy. I just would rather, keep with how they've always done it, which is everything's a 1 for this and everything's a 2 for this, rather than thinking about, okay, I've got to have a u and then I've got to have a lambda. So this is, lambda 1 is eigenvalue 1, V1 is vector for the eigenvalue 1, and C1 is the constant, right? And then all of this is constant C2 for eigenvector V2 for eigenvalue lambda 2. So it just seems a lot simpler that way. So it's up to you. Age structured means those questions where you've got juveniles and adults, etc. And you've got, xt plus 1 or xt minus 1. Okay. Now, I would think that, the last few years, they've kind of put really big, long answer questions on these. So at the end of the last section, so section L, I'll show you a great big question on this and then a great big question on the last section. And that's, I kind of anticipate you're at least going to get one of the two or maybe both again on your final, because they make you do everything, right, in the question. So a lot of people have trouble telling the two types of questions